Welcome to our final year project presentation from the Department of Aerospace Engineering at SNS College of Technology, Coimbatore. The institution is accredited with an A++ grade by NAAC and is known for its strong academic and research excellence. This presentation is part of Project II for the 8th semester, where we present our work, methodology, and key findings in the field of composite materials. This project was carried out under the guidance of Mr. N. Venkatesh, Assistant Professor in the Department of Aerospace Engineering. The team members involved in this work are Jivashruti R., Pandaiselvam S., and Tamilan S. Each member contributed to different stages of the project, including fabrication, testing, analysis, and documentation, ensuring a well-coordinated and complete study. The title of our project is GenAI-Based Mechanical and Structural Property Analysis of Hybrid Composites. This work focuses on studying hybrid composite materials through experimental investigation and analysis. The goal is to understand how combining different fibers can influence strength, durability, and structural performance in engineering applications. Fiber-reinforced polymer composites, also known as FRP composites, are widely used due to their high strength-to-weight ratio and excellent durability. In this project, we focus on hybrid composites made by combining glass fiber and jute fiber. Glass fiber provides strength and stiffness, while jute fiber offers eco-friendliness and low cost. By combining these materials, we aim to achieve both performance and sustainability. Traditional materials such as metals often have high weight and poor corrosion resistance. This creates the need for lightweight and high-strength materials in modern engineering applications. Hybrid composites offer a promising alternative by improving performance while reducing environmental impact. However, there are limited studies on glass and jute hybrid composites, which makes this research important. The main objective of this study is to fabricate glass and jute fiber reinforced epoxy composites and evaluate their mechanical properties such as tensile, compression, flexural, and hardness. We also analyze load displacement and stress-strain behavior. In addition, microstructural analysis is carried out using SEM and XRD techniques to understand the internal structure and bonding characteristics of the composite. In this project, glass fiber is used for its high strength and stiffness, while jute fiber is selected for being eco-friendly, lightweight, and cost-effective. Epoxy resin LY556 acts as the matrix material that binds the fibers together, and hardener HY951 is used to cure the resin and improve bonding. A mixing ratio of 10:1 is maintained for proper curing. Materials like peel, ply, and breather are also used to ensure surface quality and remove air during the process. The fabrication of the composite is carried out using the hand layup technique. Glass and jute fibers are arranged in 5 layers, consisting of 3 layers of glass fiber and 2 layers of jute fiber. The epoxy resin and hardener mixture is applied evenly over each layer. A matrix-to-reinforcement ratio of 45:55 is maintained. Vacuum bagging is then used to remove air bubbles and improve bonding between layers. In the vacuum bagging setup, materials such as peel, ply, breather, and vacuum bag film are used. A vacuum pressure of approximately 1 bar is applied to remove trapped air and excess resin. This process improves the bonding between layers, ensures uniform thickness, and enhances the overall mechanical properties of the laminate. After fabrication, the laminate undergoes a curing process at room temperature for about 12 hours. Vacuum pressure is maintained for the first hour and then removed. Proper curing is essential to achieve strong bonding between the fibers and the matrix. This process was supported by the Defense Research and Development Laboratory, ensuring reliability and quality in the fabrication process. After the curing process, the composite laminate of 2.5 in thickness is obtained. The specimens are then carefully prepared according to ASTM standards for different mechanical tests. Tensile specimens are cut to dimensions of 250 by 25 mm, compression specimens to 25 by 25 mm, and flexural specimens to 128 by 13 mm. Hardness samples and small sections for SEM and XRD analysis are also prepared. Proper cutting ensures uniformity and accuracy in test results. To ensure reliability and consistency, standard testing procedures are followed. Tensile testing is conducted as per ASTM D3039, compression testing follows ASTM D3410, and flexural testing is based on ASTM D7264. Hardness is measured using ASTM D2583. In addition, SEM is used to observe surface morphology and bonding characteristics, while XRD helps in identifying the crystalline structure and phase composition of the material. The experimental setup includes an electromechanical universal testing machine used for tensile, compression, and flexural tests. Specimens are properly mounted using suitable grips and fixtures to ensure alignment. Load is applied gradually until failure occurs, and data such as load displacement and stress strain values are recorded. Additional equipment like hardness testers, impact testing machines, SEM, and XRD instruments are also used for detailed analysis. In the tensile test, the specimen is subjected to a pulling force until it breaks. The setup ensures proper alignment and uniform loading conditions. Observations are made before and after the test to understand deformation and fracture behavior. This test helps determine the tensile strength and elongation characteristics of the composite material. The tensile test results are represented using load versus displacement and stress versus strain graphs. These graphs help in understanding how the material behaves under tensile loading. The curves indicate the stiffness, strength, and failure point of the composite, providing insight into its ability to withstand stretching forces. In the compression test, the specimen is subjected to compressive loading until failure. The setup ensures that the load is applied uniformly across the surface. Observations before and after testing help in identifying deformation patterns and failure modes. This test is important for understanding how the material behaves under compressive forces. The compression test results are also plotted in the form of load versus displacement and stress versus strain graphs. These graphs show how the material responds to compressive loads and indicate its strength and deformation characteristics under such conditions. The flexural test evaluates the bending strength of the composite. In this test, the specimen is placed on supports and load is applied at the center until failure occurs. Observations before and after testing help in understanding bending behavior and fracture characteristics. This test is essential for applications where the material experiences bending loads. The flexural test results are presented using load displacement and stress strain graphs. These graphs illustrate the material's resistance to bending and provide information about its flexibility and stiffness under flexural loading conditions. The mechanical test results show that the composite exhibits good performance overall. The tensile, compression, and flexural values indicate balanced mechanical properties. The load displacement and stress strain data provide a clear understanding of how the material behaves under different types of loading, confirming its suitability for various engineering applications. The hardness test is conducted to evaluate the surface strength of the composite. Multiple trials are taken to ensure accuracy, and the average hardness value is calculated. The results show a consistent hardness value of around 85.67 HRB, indicating uniform distribution of the resin and good bonding between the fibers and the matrix. Microstructural analysis is carried out using scanning electron microscopy. This technique helps in observing the surface morphology, fiber alignment, and bonding between the fiber and matrix. The images reveal good adhesion between the glass and jute fibers with the epoxy matrix, which plays a key role in effective load transfer and overall strength of the composite. Further microstructural observations using SEM show the fracture behavior of the composite. The images indicate fiber breakage and matrix cracking as the primary modes of failure. These observations confirm that the material is capable of handling stress effectively before failure, demonstrating reliable structural performance. X-ray diffraction analysis is performed to study the internal structure of the composite. The results indicate that the material has a predominantly amorphous structure with no major defects. This suggests that the fabrication process was effective and the material structure is stable. Additional XRD analysis is carried out to study thickness and composition variations. The results confirm uniform distribution of materials across the laminate. This uniformity contributes to consistent mechanical performance and reliability of the composite in practical applications. From the overall discussion, it is observed that the hybrid glass and jute composite exhibits balanced mechanical performance. The presence of glass fiber enhances tensile strength, while jute fiber contributes to reduced weight and eco-friendliness. The compression and flexural results show stable and damage-tolerant behavior. The hardness results confirm proper resin distribution, while SEM analysis shows strong fiber matrix bonding. XRD results indicate a defect-free structure. The failure modes observed include fiber breakage and matrix cracking, which are typical and acceptable for composite materials under load. In conclusion, the experimental investigation demonstrates that the glass and jute fiber reinforced epoxy composite has reliable mechanical and structural performance. The tensile, compression, and flexural results indicate good strength and stiffness, while hardness values confirm material consistency. The composite is suitable for low to medium load applications such as automotive interiors, furniture, marine components, and construction materials. Its lightweight nature, cost-effectiveness, and eco-friendly properties make it a strong alternative to conventional materials. Looking ahead, future work can focus on optimizing fiber orientation and stacking sequence to further improve performance. Advanced fabrication methods such as compression molding can be explored, and the addition of nanofillers can enhance material properties. Further studies can also include thermal, impact, and fatigue analysis. There is strong potential for developing fully biodegradable and sustainable composites. These materials can be widely used in applications such as aerospace structures, automotive components, marine parts, construction panels, and other lightweight engineering structures. Finally, the project is supported by various research studies and literature that validate the findings and provide a strong foundation for this work. Thank you for your attention.